Hello, in this video we're going to go over reactions of carboxylic acids. So it's in the name, carboxylic acids are acids. They are weak acids, however. So remember, acids can donate a proton or an H plus ion to solution. So with the carboxylic acids, if you dissolve them in water, the water molecule is going to team up with the hydrogen from the carboxylic acid, and they're going to form the hydronium ion, H3O+. Now, because we're taking that hydrogen away from the carboxylic acid, we're actually going to leave the shared electrons behind on oxygen. So that's going to make oxygen negatively charged. And we actually call this product a carboxylate ion. So notice that we went from ic acid to ate. And this is very similar to how we named esters, right? We used the carboxylic acid part and changed the ic acid to ate. So for example, down below, we've got acetic acid here, and that's what's present in vinegar. And we're going to react that with water. So in this case, water's acting as a base, and it's going to grab that hydrogen from the carboxylic acid and form H3O+, the hydronium ion, and what's left over is the acetate ion. So again, we changed ic acid to ate. Also notice that there are two arrows going forward and backward on both of these examples. So those are equilibrium arrows. So that tells us that depending on the pH of the solution, so how acidic or basic it is, we could go towards the products or towards the reactants. So we can kind of go back and forth. Now, because carboxylic acids are acids, they can also react with stronger bases. And if you react an acid with a stronger base, there's no longer an equilibrium arrow. You just have a forward arrow because the base is so strong, it really wants to react and give us those products. So for example, we could use sodium hydroxide, NaOH, or potassium hydroxide, KOH, and those are both really strong bases. So down below we have a generic carboxylic acid, and then our base, sodium hydroxide, which is really strong. And instead of water teaming up with hydrogen, here we have the hydroxide ion, which is negatively charged, and that's going to team up with our hydrogen to make a water molecule. Now again, the shared electrons between oxygen and hydrogen on the carboxylic acid will be left behind. So oxygen becomes negatively charged. So that will be our carboxylate ion. And sodium will also be left behind, and it's positively charged. So that sodium ion is going to team up with the negative oxygen on the carboxylate ion, and now we have a sodium carboxylate ionic compound. And this is also called a salt. So that's similar to sodium chloride, which is table salt. Okay, now let's look at some specific examples here. So let's say we have acetic acid, which is vinegar, and we react that with sodium hydroxide. Again, that hydroxide ion will team up with hydrogen to give us water. And then the electrons are going to be left behind on oxygen, so we get that negative charge. And sodium's also left behind, and that's positively charged, so it teams up with the negatively charged ion. So the name of this product would be sodium acetate. So we changed ic acid to ATE, sodium acetate. Below that, we have the example of benzoic acid reacting with potassium hydroxide. Same thing as above, we have our negative OH. That's going to be attracted to the hydrogen on the carboxylic acid. So we form a water molecule, H2O. Electrons are again left behind on oxygen to give us a negative charge. Potassium is also left behind and it has a positive charge, so it's attracted to that negative charge. So here we have formed potassium benzoate. So we changed ic acid to ate, benzoate. All right, so by now you probably picked up on the pattern for naming these carboxylic acid salts. So to name these salts, you're going to name the metal ion first, and then change the ic ending to ate. So the example down below, we have our metal ion, sodium, and then the rest here was originally benzoic acid, but then we just changed the ending to ATE, so it became benzoate. Now, carboxylic acid salts are really useful. They are typically solids at room temperature, but they're also soluble in water because they are ionic. So we can use them for different things. Now, down below, these aren't the carboxylic acid salts, they're the original carboxylic acids. But notice that these examples have a ton of carbons and hydrogens attached. So for instance, we have 14 of these CH2 groups, and then at the end we would have a CH3. So this is a really long carbon-hydrogen chain that's attached. However, this comes in handy for things like soaps. Soap has a polar end and then a very long non-polar end. The polar end is attracted to water, and the non-polar end is going to face away from water. So in soap, what ends up happening is these long molecules form basically like a little sphere around dirt. And then water is going to wash that away. So these are called micelles. Oops. So, we can turn a lot of different things into useful products like this. So for example, sodium and potassium salts of long-chain acids are used as soaps. One example is sodium stearate. Calcium and sodium propanoate, so those are a little smaller. Those are used as preservatives in bakery products to prevent them from going bad too soon. Sodium benzoate, which we saw earlier, is a food preservative used in ketchup and soda. And this last one, which I cannot pronounce for the life of me, zinc 10 undecolinate is used to treat athlete's foot. So if you have used products like that before, if you look at the ingredients list, you should see something similar to that. All right. So next time, we're going to talk about carboxylic ester reactions. And then we'll finally wrap up this chapter with amines and amide reactions. So I will see you then.